GraphBLAS provides a powerful and expressive framework for creating graph algorithms. The GraphBLAS vision is to create a groundbreaking transformative shift in how graph algorithms are expressed as linear algebraic operations over semirings applied to sparse adjacency matrices. When applied to sparse adjacency matrices, these linear algebraic operations are equivalent to computations on graphs. The result is a high level of abstraction in which we can easily write complicated graph algorithms while at the same time achieving a high level of performance. Analogous to how high-level packages such as MATLAB and BLAS have transformed high-performance matrix computations, we can write these graph algorithms easily in C or high-level languages such as MATLAB or Python. First, an overview of GraphBLAS itself. Consider a breadth-first search starting at node 4 with a frontier of nodes 1 and 3. The next frontier has nodes 2 and 6. This traditional algorithm is simple to state, but as graph algorithms get more complex, the node and edge centric model gets harder and harder to write, particularly in parallel. The key observation is that this BFS has the same workflow as a matrix vector multiply. Take the vector Q with entries 1 and 3 present and multiply it by A transpose. This gives the set union of outgoing edges from the frontier in green with entries 2, 4, and 6 in red for the next frontier. Node 4, however, is excluded with the if test in the traditional BFS. This translates to a matrix mask where only entries without a parent are allowed into the final result. We use the any second I semiring for the BFS instead of the conventional plus times. The multiplicative operator second I returns the row index k with a candidate parent node ID. The additive operator is the any function, which picks any valid parent. The primary GraphBLAS operations include matrix multiply, element-wise operations, extract and assign, and so on. They can all be used with a mask and with many different data types, operators, and semirings. Different semirings appear in different graph algorithms. The BFS relies on the any second I semiring. A shortest path problem uses the min plus semiring. In the next slides, I'll illustrate the Python and MATLAB code for PageRank and Betweenness centrality, which use similar semirings, plus second and plus first. That's a quick intro into GraphBLAS itself. Now to show you how easy it is to use GraphBLAS from Python and MATLAB and yet get nearly the same performance as C. First of all, the syntax is much simpler. We don't have a compiler for our GraphBLAS mathematical notation, but we write a masked matrix multiply over a semiring this way, where an accumulator operator of times is being used in this example. In the C syntax, you have to provide the entire set of arguments, even ones you don't need. These can be dropped out in Python and MATLAB. In MATLAB, the GraphBLAS matrix is an overloaded MATLAB object, and all of the MATLAB operator syntax and many built-in functions can be used with it. Here's PageRank in both Python on the left and MATLAB on the right using GraphBLAS. These are the entire functions with no details left out, even checking input arguments. First, we construct a vector R with values of 1 over n, and then compute the row degree of each node, which is scaled by the damping factor. The teleport factor defines what happens to a node with no outgoing edges. Lines 17 to 25 of both codes form the core of the PageRank iterations, a scalar to vector expansion, then A transpose times the last rank vector R divided by the degree vector D element-wise, and then accumulated back into the vector R. We use the plus second semiring. The second function is the multiplicative operator, f of x, y, is just y. Rather like 1 times y, if the values in A were all equal to 1. Betweenness centrality is a little bit longer, so I'm just showing the second phase. The first phase has summed up the number of shortest paths through all nodes. The second phase computes the centralities in a backward pass, starting at the last level here for k equals depth, and then working backwards to the source nodes. The S array is an array or a cell array in MATLAB of GraphBLAS matrices, and S of k contains the pattern of the frontier nodes at the kth level. This frontier is used as a mask when summing up the contribution of these nodes to the final centrality. For a fair performance comparison, we don't want to just compare GraphBLAS in C versus its use in Python and MATLAB. Instead, we compare against a highly tuned parallel benchmark, the GAP benchmark by Scott Beamer, which does not use GraphBLAS. The benchmark has 6 algorithms, and here we've selected 2 of them. It's performed on 5 large graphs. Note, by the way, the high diameter of the road graph. That will come up, impact our results in later slides. On the left, in this slide, are the runtimes for Scott Beamer's GAP benchmark on the left for PageRank. The second set of data is LAGraph, which uses GraphBLAS via its C interface. It's almost as fast as the GAP benchmark, just a lot easier to write the code. The third set of data is Python with GraphBLAS, and the last slide you saw, and its performance is essentially the same as GraphBLAS and almost as fast as the GAP benchmark. This is because GraphBLAS is a high-level API with very large bulk operations for constructing graph computational kernels. We don't suffer any Python interpretation by looping over nodes and edges inside Python. The same is true for MATLAB for this last set, but here we're limited by our current interface. A MATLAB function, with one exception, cannot modify its inputs, but GraphBLAS relies heavily on this. This can be done in C and Python, but not yet in MATLAB. Still, we're typically no worse than a factor of 2 or 3 from the GAP benchmark. Betweenness centrality is similar in performance, except for the road graph. Here, our C version in LAGraph is not quite as fast as the GAP benchmark. Here, the high diameter is troublesome for the road graph. You can see here. However, the key point, takeaway from this is the Python performance is almost as fast as our C performance in LAGraph. MATLAB is only slightly slower, again, because of the extra copying that has to go on. Finally, here are some comparisons just inside MATLAB. When the conventional plus times semiring is in use, the GRB objects in MATLAB, in the GraphBLAS interface to MATLAB, can use operator overloading. So the syntax is identical to MATLAB. C equals A times B. It's just way faster in GraphBLAS, 30 times faster for matrix multiply. Now, as a caveat though, I wrote the single-threaded A times B inside MATLAB for the MathWorks many years ago. So I'm competing against myself. This is now a parallel version on 20 cores. I got a 30x speed up. Submatrix assignment can be done both in MATLAB and in GraphBLAS. It's just faster, up to 2 to the 1,000 times faster in GraphBLAS, and plus more types. You have sparse integers, for example. MATLAB can't make these matrices this big, but you can do it in GraphBLAS. And the masked assignment, this statement right here exists in MATLAB. You can do a mask with a logical matrix in MATLAB, and using a logical matrix M that's the same size as C, you can do the same thing in GraphBLAS. It's just way faster in GraphBLAS. That's not a type, but that's 100,000 times faster. 7 seconds versus over a week. So in summary, to wrap up, GraphBLAS is a powerful abstraction for writing graph algorithms based on the elegant mathematics of linear algebra over a semiring. It gives you easy to write yet fast algorithms, even in C, and it's even easier to write algorithms in it in Python and MATLAB. The performance is close to that of a highly tuned parallel kernel in C, particularly in the Python interface, which do not use GraphBLAS. But these are these highly tuned parallel kernels are much harder to write for a data scientist. When writing an algorithm in GraphBLAS, Python is just as fast as C. MATLAB is a little slower because we have more memory copies going on. We're addressing this with some help from my colleagues at MathWorks. Python and MATLAB both allow the end user to skip some of the details that the C API exposes. So now Python and MATLAB with GraphBLAS provide new tools to end users, making it very easy to write complex graph algorithms. Similar programmability and performance gains could be obtained in Julia, Java, Rust, Octave, and we have many of these in progress already. So for more details, go to graphblas.org or come to the Birds of a Feather session tonight. Thank you for your attention. Any questions?